Okay, so let's chit chat about a couple of these problems that Notorious can give you fits. Let's talk about the, in kind of comparing and contrasting questions 7 and 8, okay? So on question number 7, here's the setup. You're standing on top of my table and you're just going to fall. So, and this is going to be so important as you begin to understand kind of these complex problems. Me dropping a ball with an initial velocity of 0 is mathematically the same as me throwing a ball and it reaching its maximum height and starting to fall from 0, okay? So a ball thrown up here that hitting 0 and starting to fall is mathematically the same as you just jumping off a table or something falling. Because in both situations, the initial velocity is going to be 0. So this is where you have to pay attention to the signs and the subtleties of physics. So, because you're just going to fall, what's your initial velocity? 0. Okay? And one of the most vital things, as odd as it may seem, is that differentiation between your initial velocity and your final velocity. Now, what are you trying to ultimately find? How long and how fast you're going, right? You don't have time. So what are you going to use to find the velocity? What's one equation that doesn't involve time? That equation. So you know v squared equals v naught squared plus 2ad. Okay? Conveniently, your initial velocity is 0. Don't have to worry about that. Okay? So basically you have the square root of 2ad. This is where the subtle parts of physics play into this. So you've got 2 times negative 9.8 meters per second squared. Now, you're 0.7 meters. If you just put 0.7 meters there, technically, what are you going to end up with underneath that radical?
Negative.
Which means you're led to imaginary velocity. Okay? It's subtle, and you're going, God, Burkham, don't you have anything better to worry about than a negative sign underneath the radical? Seriously, get a life. People have been saying that to me for a long time. But here's the reality. It boils down to, do you actually understand this system? Do you understand how physics works? Do you understand frame of reference and how things are defined? Yes, you could ignore it and just act like everything's positive. I won't know the difference in that particular problem. But what's going to happen is that later on when you get into more complex problems and you're used to just taking that shortcut, you're screwed on the complex problems because you're not going to know what to do. So the sooner that you embrace, hey, this has to be a consistent methodology, the more complex problems become much easier to work. Okay, so you do this, you're going to get a number, should be around 4 meters per second. Okay, so you're going to go about 4 meters per second. And don't get hung up and go, oh, your velocity is 0 because you hit the ground. No, it's right as you hit the ground, okay? Do not tell me, oh, the final velocity is 0 because you hit the ground. It's how fast you're going when you hit the ground. Now, let's talk about the time calculation, okay? This is a wonderful equation, and you need to embrace this equation when things begin to fall. Because you're falling, what's your initial velocity? 0, okay? That goes away. You solve this for time, you get 2x over a, the square root of that gets you time, okay? This is not a big dog equation, but it's certainly one of the biggest like sub-equations that you can have. Become one with this equation. It's a great equation, but listen to me. It only works if the initial velocity is 0. If I throw it up in the air, I can't use this equation because then my v naught term doesn't drop out, okay? But if I drop it, or even if I throw it up in the air and then have it fall from its highest point, I can use this equation. It's wonderful. Embrace it. Become one with it, okay? So, in this situation again, and you're gonna have a big complex problem on the test. And if you put 0.70 meters divided by negative 9.8 meters per second squared, and this is what you put on the test, and I'm gonna go through every calculation on your test. And if you do this, I am very snarkily gonna write, imaginary. And then a big question mark, and then put nice. How sarcastic do you think that is? Very, dripping with it, oozing sarcasm. However, if you make one subtle change and you make that a negative value, because that's what it is, it's displacement. Now what happens?
It's not
Now it's not imaginary, now you have two negative signs underneath the radical. Again, it's subtle, but it's important in terms of how you view the problem. Now, in contrast to that, you have problem number 8. So in problem number 8, if you're ever driving in the outback of Australia at night, do not hit a kangaroo, it will completely jack up your car. So instead of like bull guards, they have roo guards. Okay, so there's a horribly drawn kangaroo. Okay, I teach physics now. There's a kangaroo. Kanga the kangaroo. So, Kanga the kangaroo is going to jump up in the air. Now, here's the difference. If you look at v squared equals v naught squared plus 2ax, in this particular problem, what are you solving for? The initial velocity or the final velocity? Initial. Because what's the final velocity of the kangaroo at its highest point? 0. You know the final velocity. You're trying to find the initial velocity. So I beg of you, solve these equations before you put in the numbers. Oh, I need to get v naught. Oh, that's going to be v squared minus 2ax, and the square root of that is going to equal my v naught. Now, again, this is subtle, but it's vitally important. So, what's my final velocity of the kangaroo at its highest point? 0. Okay? Now, this is important because I'm going to have 0 squared minus 2 times negative 9.8 meters per second squared. But what is my x value? Is that x value a positive or a negative number?
Positive.
It's a positive number. But that's cool, okay? That's cool because you're going up. But again, this is where this works. I have 0 minus a negative number, which makes it positive. So it all fits, okay? You don't have to randomly go, man, I got an awkward negative sign. Okay, there, problem solved. I'll just erase it, okay? No, if you find yourself randomly marking out negative signs, bad, something is wrong, okay? You define something wrong. So, your initial velocity on number 8 should be around 5 meters per second, okay? Here's what's going to happen. You're going to do all of this, and you're going to be so excited that you remember the negative signs, and then you forget to take the square root, okay? Been there, seen it, it happens.
Don't be silly, Mr. Burkamp. I would never do that.
I know, I see. And you would never forget your water jug either.
No, of course not.
Of course not. Okay, now, on number 8, when I ask you to draw the velocity vectors. So, here's Kanga the kangaroo jumping up in the air. What are the only two things that can happen to that velocity vector?
Bigger, smaller.
They get bigger, they get smaller. He's going up in the air. What's going to happen to the velocity vectors? So I just come in here and go, okay, hey, there's V2, there's V3. That's all you got. So which direction are my acceleration vectors going to point?
Down.
Down. There's my negative acceleration. When the Kanga starts to fall, what happens to his velocity vectors?
Bigger.
And they point,
Down.
so there's V1, V2, V3. Do my acceleration vectors switch sign? No. Which direction do they point?
Down.
Down. Which is why my velocity time graph looks like this. Okay? With that same slope of negative 9.8 meters per second squared. Cool with that. Now, ironically, let's talk about question number 11. So did some of you get hail last night?
I have no
I got
idea.
to while I was doing the problem, it freaked me out so much.
I can see that.
I was in the middle of doing this when I felt like a phone on my window, and I just jumped on my tree.
That's never happened in all the years of assignment, this particular question. So the actual terminal velocity of a hailstone is about, depending upon the shape and mass, between 20 and 25 meters per second. Okay? So if you see how much damage hailstones do at 20 to 25 meters per second, imagine they actually hit at 400 and some odd meters per second. Number one, it can't happen. So physicists are famous for just ignoring things that annoy us, okay? Air resistance, for example. In reality, as soon as something falls and it speeds up, your acceleration is no longer negative 9.8. But that just gets ugly, so we just assume that it is. So hailstones, it kind of becomes a catch-22. Hailstones fall through our atmosphere, and that creates air resistance, and that's they actually get slowed down. But without an atmosphere, you wouldn't have weather and you wouldn't have hailstones to begin with. So it's like you have to have an atmosphere to have hailstones, so you automatically have some wind resistance too. So yeah, if you've seen what damage it did at like 25 meters per second, keeping in mind the speed of sound is 340 meters per second, these things would actually, if they could fall that fast, would actually be going faster than the speed of sound. It would not damage your car, it would go through your car, okay? It would physically go through your car. Because we'll study kinetic energy later. Kinetic energy is 1/2 mv squared. You're squaring the velocity of 425. That's a big number, okay? So thank God we have air resistance to slow hailstones down. On 12A, because if 12A is wrong, everything is going to go wrong. So 12A and the question with the kangaroo on number 8 are the exact same idea. The only difference is that you're talking about throwing it up on the moon and Earth versus a kangaroo. It's the exact same idea. So your answer to 12A should be something very close to, listen to me very carefully, the legal drinking age. Okay? Not what you think it is on prom weekend when your folks are out of town. Okay? Not that any of you would do that, but I'm just saying. Make sure on number 12C, when you're drawing that graph, you should have 2 lines, an earth line and a moon line. Make sure I know which one is which. Okay? Make sure I know which one is which. Now, let's talk about number 15. So 15 can be a little bit frustrating because it's like, hurricane, man, we don't have numbers. What is this H stuff? Seriously, who deals in H's? Well, we do. So the whole key to this problem is that you're going to drop something, right? Since it's going to be dropped, what equation can you use to find time for something that is dropped or is falling from a maximum height? Time equals the square root of 2x over 8, right? Because it's fun. This is what you have to start with, okay? So the first height is h. So how can you find the time for the smaller height? What would you plug in? 2h over 9.8 meters per second squared, right? So you would do. Now, technically the h is negative and technically the negative 9.8 are negative, so we're just going to go and simplify that and make everything positive. So here's where the magic happens. Can I write that as the square root of 2/9 times the square root of h? Is that legal mathematically? Absolutely it is. Absolutely it is. Okay? Absolutely that is. So could you actually give me the number of the square root of 2 over 9?
Yes.
Somebody do this. Somebody take the square root of 2 over 9.
0.471.
What'd you get?
0.471.
0.471? No, you don't.
It's like 0.45 something?
Yeah.
Wait, 2 divided by 9.
2 divided by 9 and then the square root of it.
Well, it's not, isn't it 9.8?
Yeah, I'm getting.
Excuse me, 9.8, I'm sorry, that's 9.8, my bad. That's 2 divided by 9.8, I left off the 0.8, that's on me. 0.45, what? 2. Times the square root of h. So, here's the beauty of this, is as soon as you know what h is, this is gonna give you the time. So if the height is 1 meter, you just plug in, the square root of 1 times 0.452, it's going to take 0.452 seconds. If h is 2 meters tall, you would put in 2, the square root of that, multiply that by 0.452. Okay? So you can plug in any value of h. That's the beauty of this equation. So now the next one is going to be 5h, right? So we're going to have time equals 2. But instead of x, what are we going to have? 5h over 9.8 meters per second squared. Well, what's 2 times 5?
10.
So can I write that as the square root of 10 over 9.8 times the square root of h? Is that cool?
Of course.
Could I get that number? 1.01. So can you just subtract those values? Yeah. So the time difference is going to be 1.01 times the square root of h minus 0.452 times the square root of h. And then you automatically already have it in terms of an expression of h. So then if you know what h is, 1 meter. You plug that in, that tells you that ratio that you need. Okay? So when things fall, you remember this on the test tomorrow. Okay? When things are dropped, that's how you find time. Okay? Just saying. Now let's talk about question 46 out of the book, because this is important conceptually. So, on that question on 46, it's got student at the top of building H throws ball straight upward, and ball B throws downward at the same initial speed compared to the ball's acceleration. So, keep this in mind. If I just drop the ball, as soon as I let go of it, what's the only force acting on it? What's the acceleration? 9.8. If I throw it up in the air, as soon as it leaves my hand, what's the only force acting on it? What's going to be the acceleration? You see a pattern. If I throw it down, as soon as it leaves my hand, what's the only force acting on it? What's the acceleration? Negative 9.8. Okay? Now, when you look at v squared equaling v naught squared plus 2ax, this is going to be important later on when you get to energy. Situation number 1, I throw it down at negative 10 meters per second. It's going to have a certain acceleration, it's going to travel a certain distance. Okay? And that's going to be the distance from where I let go of it. So if I throw it down, I'm going to have negative 10 squared plus 2ax, right? If I throw it up in the air at 10 meters per second from the same height, mathematically, am I going to get the exact same answer? Sure I will. Negative 10 squared plus that, negative 10 squared gets you what? 100. If I take 10 squared, I get 100. In both situations, it's going to land with the exact same velocity. The direction that I throw it does not matter as long as I throw it from the same height. Are they both going to have the same acceleration? Are they both going to travel the same distance? In both situations, keep in mind this is v naught squared. So does it make any difference if that would be positive or negative? No, because it is squared. Okay?
Is this for a certain question?
It's for question 46.
Oh, okay.
Okay? To question 46.
So, velocity. So the velocity is the same. And, well, yeah, it's up there. Man,
Because v squared equals v naught squared plus 2ax.
I wrote a lot of that wrong.
Okay, now let's talk about number 16. The only way you can do 16a is to do x equals 1/2 at squared plus v naught time. Okay, that's the only way you can do number 16 to find that height. It's a function equation. You know the time, you know the acceleration, you know the initial velocity. It's a function equation. You can plug in any value of time to find out the height. So your answer to 16a should be around 130 meters, right? Which is up there ways. That's like a football field and throw it up in the air. And if you're designing pyrotechnics, that's what you want, okay? You want them to explode up in the air, ooh ah, okay? To get the velocity, what you cannot do to get the velocity oh, my computer has been my nemesis today. Hold on. What you cannot do to get the velocity is use that equation. Mainly because of the fact that you don't know if it's on the way up or if it's on the way down. We're back. Cool. So, do you know the final velocity of the mortar is 0?
No.
No, you don't. That's the whole point. You don't know what the final velocity is. So the only way to get that final velocity is to go v equals v naught plus at. It's a slope-intercept form. You're starting here at 50 meters per second. Lines coming down like that. That's 0. You're just trying to find the y value that corresponds with 5 seconds, knowing the slope of the line is negative 9.8 meters per second squared. Okay? So obviously if your velocity is positive, which direction is it going?
Still going up.
It's still going up. If your velocity is negative, it's on its way down. Okay? Cool with that. But sure that you can do that problem. Now let's talk about the elevator problem on number 17. So, obviously when you walk in the elevator, hopefully, what's the initial velocity of the elevator? 0. Okay, that's kind of cool. Okay, elevator, you got to jump on a moving elevator. Sketchy. Yeah, what could possibly go wrong? Especially if grandma's in a wheelchair. Ready, grandma? Pam! Okay. So, assuming the initial velocity is 0. Elevators that don't accelerate don't sell very well. It's like, what does your elevator do? It's just a door that opens and closes. Does it move? No. But it has really nice doors. Okay? Not going to sell very well. So, on your velocity time graph, what's that going to look like when it's speeding up?
Slope up.
Straight sloping line. Okay? Now, the elevator is accelerating during that time. True? And you're told that it can accelerate up to like 2 meters per second squared and reach a final velocity of what, like 6 meters per second? I don't know.
Something like that. Yeah.
Yeah. So, think this through. If you can accelerate at 2 meters per second squared, which is a rate function of change in velocity, how long is it going to take for you to get to 6 meters per second? 3 seconds, because you go from 0 to 2, 2 to 4, 4 to 6. So you know this is going to be 3 seconds. And you know at that point they're going to be going 6 meters per second. Could you find the area of that little triangle? What would that represent? How far it goes while the elevator is accelerating. Okay? Now at this point, what's the elevator going to do? Move at a constant velocity. So what's the graph going to do? It's going to move as a horizontal line. True?
True.
Eventually, what does the elevator have to do?
Slow down.
Slow down. Again, jumping off moving elevators, not so cool. Approaching third floor, get ready to jump, the doors are gonna open. So what's gonna be the slope of that line? Negative 2 meters per second squared. Do you think those two areas are symmetrical?
Yes.
Yes. So if you can find this area and that area, that gives you the area that the distance traveled while it was accelerating. What's the total distance the elevator has to move? 200 meters. So if you subtract out these two areas, what do you have left? Yeah, you have the area of that rectangle. You have the area while it's traveling at constant velocity. Now, since it's traveling at constant velocity, this is the one time on this assignment you can use distance equals velocity time. Do you know, so this distance is going to be the 200 meters minus the accelerated distances. Okay? You know the velocity is 6 meters per second. You can figure out how long it takes to travel that. Add the two times together. Your answer to 17D should be in the mid 30 seconds. Like that. See what happens when you bring your folder? It's in the middle-ish.
So the one place is about Gershon's GPA, would you say?
Huh?
The one place would be about Gershon's GPA.
Yeah.
Can I divide like all of the numbers?
Could you say 30 plus Gershon's GPA? 30 plus is like
Yeah,
6.
Sean.
About Gershon's GPA.
Okay.
Wait,
So 6 times.
Your answers to 9 and 10 on the ones that I gave you, both of those should be like around 30 meters. That's a huge ish. Okay? That's an ish, but they should be in the 30s. On number 3, with the launch and landing at the F-18, the launch acceleration should be in the mid-30s. The landing acceleration should be in the mid-20s. Question number 3.
wait, did you say what that?
Huh?
Is there the
The launch is in the mid-30s.
Okay.
The landing is in the mid-20s. Okay? Any other questions? Now, if you want to hold on to this assignment and hand it in tomorrow and keep it to study, that's cool. If you're done and you want to hand it in, you can do that too. It's whatever works best for your study pattern. Okay? That's completely up to you. Hand it in, keep it, whatever that you want to do. But if you keep it, don't lose the pages. I know, but I'm just saying, I can see that happen.
Yeah.
It's been $100 something.
Oh, yeah, I think my psychology teacher was no, I was joking. I mean, she asked how much.
Ava, can you stop that camera?